Assalamualaikum warahmatullahi wabarakatuh. Welcome to Electronics. I am Madam Rosmina Zwin Abdul Rahim. To get the blessing from Allah, let's have a look on this hadith. Abu Hurairah reported, the Messenger of Allah sallallahu alaihi wasallam said, "Whoever is asked for knowledge and he conceals it, Allah will clothe him with a bridle of fire on the day of resurrection." Source Sunan Al-Tirmizi. This hadith is important because it's related to knowledge, and sometimes people come to us to ask us to teach them in anything. On something that we know, but sometimes in certain cases we tend to not to teach them, to conceal whatever that we know, and it's actually not good because as mentioned in this hadith, Allah will punish those who are doing so with the hellfire. Na'udzubillah min zalik. We are still on chapter 5, BJT-AC analysis. This video is related to chapter 5C, which has two subtopics, mainly on common collector amplifier and its related examples. If you recall, before this we have discussed on common emitter amplifier. Now we come to another configuration which is called common collector amplifier. So in opposite to the common emitter amplifier, for common collector, the output now is measured at the emitter terminal, while the gain is actually a positive value. So this is the example of common collector amplifier. So as we can see from here, we have collector, base and emitter terminals. Now we know output voltage is being measured at the emitter terminal, so we know this is a common collector amplifier. In this case, the gain should always be positive. So as usual, in order for us to do the AC analysis of any amplifier circuit, we always start with the DC analysis, because at the end of the day, we want to know what should be the current values, okay, because these current values then will be used to find for the small signal parameters, normally the RPi, GM and R0. So the same thing goes for this particular example, where we do the KVL to find for the IC, then later we can find for the RPi, GM and R0. So after we are done with the small signal parameters, the RPi, GM and R0, normally we need to redraw the small signal equivalent circuit. We need to draw the small signal equivalent circuit for us to do the AC analysis. So similar to the common emitter amplifier before, normally we start with the BJT model, where we have the base to emitter terminals, we have RPi, between collector to emitter terminal we have GMVBE, the current source, and in parallel to it we have R0. Okay, then of course after we are done with the BJT model, we can proceed with the remaining components. In this case, as you can see here, at the emitter terminal we have RE between emitter to the ground, and obviously we have R1, R2 here, which is actually RTH between base and the ground. And remember, capacitor being short circuit, so that's why we are having RS and VS. So the same thing in small signal equivalent circuit, we have RS and VS. And another thing that you should take note is we have the collector terminal, right? At the collector, it is being connected to VCC. But since VCC is grounded in AC analysis, obviously here collector is connected to ground. Okay, then in this particular amplifier circuit, output is being measured at the emitter terminal, because we are talking about common collector amplifier. But the tricky part here is actually we cannot proceed doing AC analysis just using this small signal equivalent circuit. Why? Because if you see this particular circuit, we have two ground levels. We have two ground levels here at the bottom side, and as well as here at the collector side also we have two ground levels here. Okay, so because of that, we need to modify this circuit first in order for us to proceed with AC analysis. So basically what to do in redrawing the small signal equivalent circuit, basically we need to make sure that all grounds should be connected together. So as mentioned just now, the ground level we are having here at the collector terminal, as well as here at the bottom ground level. So in this case, we have to connect them together to make them both at the same level. So what we are supposed to do is actually the base side, at the base side here, at this side, nothing is changed. Okay, it's just maintained as usual. So as you can see from here, at the base side we still have the RTH, we have the RS, we have the VS. Okay, still maintain the same. But if you see later, okay, now the idea is we want to bring the collector at the ground level here. Okay, because here is the emitter, here is the real ground level. So now because collector is grounded, we try to bring the collector here at the ground level. Okay, so meaning to say we have to rearrange a little bit, making this X, basically it is the emitter terminal, to be at the above level, and somehow we need to flip the network, I mean the circuit, by making the collector now at the bottom. Okay, so maybe you can have a look here. Just imagine you focus on the X here. Okay, focus on the X. So now at the X here, basically, okay, and this is the bottom level where we try to bring the collector at the bottom level. So remember, collector is grounded, so at the X here we have RE between X and the ground. So as you can see here, we have RE between X and the ground. Then what do we have next? We have at the X here also we have R0 between X and the collector, which is grounded. So that's why we can put here R0 actually in parallel to RE, where R0 is between the X and the collector, which is grounded. Then what do we have next? Remember, we have this beta IB or GMVBE, just the same thing, but by looking at the arrow we notice that the current is from the collector to the X, okay, or the emitter terminal. Okay, so the current is flowing from collector to the emitter, so that's why we can rearrange, but obviously in this case the direction of the current is from collector to emitter, so that's why the arrow now is pointing up, because we are bringing collector to the bottom level. Then obviously since we have rearranged it, what happened to our R pi? R pi, as you know, it is between base and the emitter terminal, right? Base and the X point there. So obviously here we have R pi between base and the emitter terminal. So this is basically the modified small signal equivalent circuit, okay, by having base, emitter and collector at the bottom. Why collector at the bottom? Because collector now is grounded. Now we have the modified small signal equivalent circuits, where now we have the base, emitter and collector at the ground level, and it's just the same thing, similar to common emitter amplifier for the AC analysis, where we are going to focus on the box here, okay, to represent our amplifier here into the voltage amplifier model, okay, because we need to take into account the RI, R0 as well as the AVVI to represent the voltage amplifier model. Here basically are the steps that we can take for us to do the AC analysis, where we always start with the output side, where we start by finding for the equivalent resistance at the output side, Req. Then later we can get I0 in terms of VBE, which is given by this. Okay, I will show you why. Then from there obviously we can get the V0 equation. Then later we proceed to the input side, because we want to relate RIB to the RI, which is later we need to get the expression of VBE in terms of VI, but this time we are using super mesh. Now let's have a look in details what are the steps that we need to consider. First, we need to find for the equivalent resistors, okay, which is Req. Please take note, normally in common emitter amplifier, the first step normally we find straight away the output resistance. But since here in common collector, we already modify the small signal equivalent circuit, meaning to say whatever resistor value that we are getting here from the output side actually is not straight away equals to the output resistance. Okay, so it's not output resistance, but meaning to say we need to find the output resistance later, at the later stage of this analysis. But at the moment we are looking for the REQ, the output resistor equivalent circuit. Okay, so in this case we simplify the whatever resistance at the output side, REQ is given as R0 in parallel to RE. Okay, then later step number 2, we need to find for I0. Okay, we need to find for I0. So in this case, as we know here, we are having one, this is our I0. Okay, then obviously from here we are having IB and IC, which is contributing for our I0. Okay, current at the emitter terminal, the output current. So that's why if you see from this, at this particular point we can make a KCL equation where GMVBE actually refers to the current flowing from the collector here, GMVBE, okay, plus the current flowing through the RPi, which is given by VBE over RPi, okay, because this is IB actually, this is IC, this is IC, and this is IB, which is later we can factorize it in terms of VBE over RPi, leaving our equation in this form. Later, step number 3, we can get the V0 equation simply by V0 is given by I0 times REQ. Okay, so step number 1 and step number 2, we multiply it so that we can get the V0 equation from there. Then step number 4, basically we need to find for RIB, and this is common. RIB is just about the same thing that we managed to consider from the common emitter amplifier, where it is given by RPi times 1 plus beta times R0 in parallel to RE. And then later from there we can relate RI to RIB, because RI is actually RIB in parallel to RTH. Okay, RI, basically this is RI, is the resistance which is equivalent to RIB, okay, in parallel to RTH. And later we can relate VBE in terms of VI using super mesh. Okay, still remember super mesh? Maybe you need to recall later, but basically using super mesh we can somehow relate VI with VBE and V0, which next slide I will show you in details. But at the moment, you know, VI is given by VBE plus V0, and in this case VBE is VBE, and V0 we have it in terms of VBE from step number 3. So from there you can actually sum it up together, leaving your VBE in these forms. Okay, your VI in terms of VBE. Then later from step number 7, remember we consider for every VI equals V0, and in this case V0 we already know. Okay, V0 we already know the equation value from step number 3. Then from there you can replace the VBE terms here, in terms of VI. We are replacing VBE in terms of VI from this equation. Actually substitute accordingly. Okay, then later you can cancel out the VI, leaving the open circuit voltage gain in this form. Okay, I think later when we do the example, we substitute all the values, it will be much easier for you to see. Okay, before we proceed, this is just a recall. This is super mesh, where super mesh is defined as the combination of two meshes which have current source on their boundary. So remember, for this particular case, we are having the current source GMVBE. Okay, so that's why we can consider this as one big KVL equation involving current source in the middle. Okay, so now for this particular example, we just repeat the steps just now, but now we try to substitute all the values, okay, so that you can have a look much better. So for the first step, remember I was saying we need to find for the REQ, okay, basically the simplified version of resistance at the output side. In this particular case, it is given by R0 in parallel to RE. Then step number 2, we need to consider KCL to get I0 in terms of VBE, basically I0 in terms of VBE. So in this case, I0 equals whatever current flowing here, okay, this is at point X, we do KCL, and plus whatever current flowing through the R pi. Okay, so we may consider this as IB, consider this as IC. So I0 is actually given by IC plus IB. IC is GMVBE and IB is actually VBE, okay, VBE over R pi. Okay, in this case, we know the GM, we know the R pi value, leaving our I0 in terms of VBE. Then obviously step number 3, we get the V0 equation basically by having this V equals IR. So we already have I0 from step 2, REQ from step number 1, substitute everything, then we are having V0 in terms of VBE. Then later for step number 4, we calculate for RIB. Where is RIB? Which is the input resistance looking at the base. In this case, it's similar to the common emitter amplifier. RIB is given by R pi plus 1 plus beta REQ. So in this case, you just substitute everything that we know. For this particular example, RIB is given by 201.24 kilo ohm. Then step number 5, once we know the RIB value, obviously we can relate it to RI, our input resistance, where RI is actually RTH in parallel to RIB. Substitute everything, you can get the value. Then step number 6, we try to relate VBE in terms of VI. Okay, so using what? Using super mesh. So if you see from the super mesh here, we are having VI, then we are having VBE across the R pi here, and we are having V0, okay, basically across the REQ here that we already found. Okay, so basically if we do some kind of KVL over the current source here, we can say negative VI plus VBE plus V0 equals 0. Okay, so that's why from here we can get VI is actually equals to VBE plus V0. VBE is VBE and V0 we already have in terms of VBE in step number 3 just now. So sum it up together, we are having VI in terms of VBE. Then later obviously we want to fit into our voltage amplifier model. We consider AVVI equals V0, where V0 we already have in terms of VBE, remember? Okay, then VBE also we have in terms of VI just now, right? So we replace accordingly. In the end, we can cancel it out, all the VI, leaving our open circuit voltage gain is 0.9837. We are not done yet. We just found for all the three important components, RI, the R0, the REQ, basically, then the AVVI. Okay, then later obviously we can consider for the sources and the load. Remember, after we are done with the voltage amplifier model, we can consider for the source and the load. So to find for the new voltage gain, where V0 over Vs, we need to consider it with Vs. Okay, so that's why you connect it together. Then step number 6, we can have Vi in terms of Vs. This one is just similar to common emitter amplifier before, where we can do the voltage divider for this particular loop, right? We do voltage divider, then from there we can get Vi in terms of Vs. Then obviously step number 7, for this particular example, okay, take note for this particular example, we don't have the load resistor, meaning to say we can still use V0 equals AVVI, meaning to say at the moment we don't know yet the R0 value. Remember I was saying just now the resistor value that we are looking for before this at step number 1 is just REQ. It's not the output resistance representing the voltage amplifier model yet, but it does not matter for us to find it now because we don't have to do any voltage divider in the output side because V0 is just given as AVVI because it's open circuit, right? Open circuit V0 equals to AVVI here, so nothing to do with R0 value. So that's why you can just simply replace AV that you already found from step number 5, then VI in terms of VS, leaving the voltage gain here in this particular case V0 over VS equals 0.962. Take note, for common collector amplifier, actually it is not a good voltage amplifier because as you can see here the gain is about close to 1, right? So as if the signal is not being amplified. Okay, but common collector actually is a good current amplifier. So as I mentioned just now, for common collector, the voltage gain normally is just close to 1. Okay, so it is not a good voltage amplifier. So that's why it's just called as voltage follower, meaning whatever input voltage you have is about the same output voltage that you are going to get. But this circuit has a very great potential as a current amplifier. So that's why from here, we want to see what should be the current gain. Okay, so let's have a look on related examples under subtopic number 2. Okay, so we are going to consider both uh, voltage gain and voltage gain for us to see related to this common collector amplifier. So as you can see from here, you straight away know this is common collector amplifier because as you can see here, the load resistor is being connected at the emitter terminal. Okay, so this is common collector amplifier, meaning to say whatever gain that will be calculated from this particular circuit should always be positive. Meaning if you are getting negative value, obviously your analysis is wrong because the gain should always be positive. Then for this particular example, obviously all the parameters for this are given, where beta given, VBE on given as this value, VA is given as infinity, meaning we don't have to consider R0 because R0 is infinity, and in this case VTH and RTH are straight away given to you for you to do the DC analysis. Then you are supposed to calculate for the IC, collector current, meaning we have to do the DC analysis first, then from there we need to draw the AC equivalent circuit, then obviously from there we need to find for the voltage gain as well as the current gain. So let's start with the DC analysis. Since RTH and VTH values are being given, so straight away we substitute in our KVL equation. I don't want to discuss in details this because I believe you already know from common emitter amplifier it's just about the same thing. From there you can calculate for IB, then obviously IC, then obviously from there we can calculate for R pi and GM. Since VA is infinity, obviously we don't have to consider for R0. Then we need to consider the small signal equivalent circuit. Remember, now common collector amplifier, we need to consider collector at the ground terminal. So this is the modified small signal equivalent circuit already. So make sure you do your own self-revision on how to do this modified small signal equivalent circuit. Make sure you do it correctly. Then from there you can actually just get the same thing. Then we start with the step 1 where we find for REQ in this case, but since we are not having small R0 because it's infinite, so in this case REQ straight away equals to RE. Then step number 2, remember we need to use KCL to get the I0 in terms of VBE, right? So I0 is equal to GM VBE plus VBE over R pi. Remember, this is the IB, this is the IC. So substitute everything that we know, leaving our I0 in terms of VBE. Then obviously step number 3, we get the V0 equation simply by V equals IR. So from there we can get V0 in terms of VBE. Later, for step number 4, we find for RIB. In this case, RIB straight away given by this formula. Substitute, you are supposed to get RIB. Then later, we can get RI, where RI is actually equals to RTH in parallel to our RIB. Then step number 6, remember we do super mesh, where VI equals VBE plus V0. VI is here, voltage here. VBE is the voltage here. V0 is the voltage here. Okay, so we do some kind of KVL over the voltage source. So that's why here in this particular case, we can have VI in terms of VBE, or we can rearrange VBE in terms of VI. So later, obviously, we try to fit to the equivalent circuit of a voltage amplifier model. Then we need to consider AVVI equals to V0, similar to common emitter amplifier before. Then V0 we already have in terms of VBE from step number 3. Then VBE we replace in terms of VI. Okay, we replace so that we can cancel out the VI, leaving our open circuit voltage gain is 0.97. Okay, for this particular example, if you notice from the circuit given before this, we have a load resistor. So in order for us to solve for the voltage gain, we need to do voltage divider in this loop. Obviously, in this case, we need to find for the output resistance value R0. We need to consider R0, so that's why we have to calculate for R0. Then how to get R0? Basically, we need to consider some kind of test voltage Vx with current Ix. So in order for us to derive for the R0 value, we need to introduce test voltage of Vx in the circuit. So as you can see here at the output side, we have Vx with a current of Ix. So in this case, R0 should be equals to Vx over Ix. But take note, in doing so, actually whatever voltage connected at the input side, we need to turn it off. Okay, so there is no Vs here, we turn it off. Okay, then basically step number 1, we need to relate VBE in terms of Vx. VBE in terms of Vx. So if you see from here, since Vi is being turned off, replaced with short circuit, meaning to say RTH here in parallel to it also won't give any effect because it's in parallel to a short circuit. Then if you consider the outer loop here, actually you can see actually plus VBE plus Vx equals 0, right? Plus VBE plus Vx equals 0. So that's why we can say VBE is actually equals to negative Vx. Then you can use nodal analysis where you can see that at this particular node, we have the current Vx over R0. This current Vx over R0, and we have current Vx over Re, this current, and we have Vx over R pi. We have Vx over R pi, okay, which is equivalent to GMVBE, because this is in opposite direction, right? GMVBE plus the Ix. GMVBE plus Ix. Okay, then from there actually remember VBE can be replaced with negative Ix. We can rearrange, okay, because at the end of the day you are supposed to get R0, which is Vx over Ix. If you rearrange this equation, you are supposed to get Vx over Ix given by R pi over the 1 plus beta in parallel to Re, which is in parallel to R0. So for this, you may go through the derivation of it, or straight away you can memorize, or you should take note that R0 is given by this formula. So coming back to our example now, we can now calculate for R0, right? Because we know the formula already, where R pi, Re, RTH and small R0 are given. So substitute everything in the formula. You are supposed to get R0 is by this value 0.03 kilo ohm. Then obviously later we can relate Vi in terms of V1 in this particular case. For this particular example, Vi equals to V1. Straight away we don't have to do the voltage divider because there is no resistor here. We straight away say Vi equals to V1 here, okay, because they are in parallel. Then later we consider the output side. In this case, this is our R0, okay, where we already found from the formula. This is our RL, the load resistor. In this particular step, we cannot say V0 equals to AVVI anymore. Okay, why? Because now we have a load resistor. So that's why in this case we need to do voltage divider. So that's why we need to find for the R0 value, because in voltage divider we need to consider R0 as well, right? So you do voltage divider to find for V0. Then later substitute AV, you already found just now, and VI actually replace it with V1. Okay, then obviously for this particular example, V0 over V1 equals to 0.963. So as mentioned before, it's not a good voltage amplifier because the gain is close to 0.963. So let's see if common collector amplifier is a good current amplifier. So obviously we want to know what should be the current gain. So for this particular example, we consider for the output side, where we consider for I0. In this case, I0 is actually V0 over RL, V0 over RL, V0 over 4. Okay, then for the input side, II, which is the input current, actually equals to V1 over Ri. Okay, then we already know the RL and Ri, substitute, leaving our I0 and II in terms of V0 and V1. Okay, so in this case, I0, you already know it is V0 over 4. This is our I0. Then our II is actually V1 over 13.55. okay, so you substitute accordingly. Then if you rearrange, you notice that we have V0 over V1 here. Okay, we have V0 over V1, which is actually our voltage gain, okay, which is the voltage gain that we already found just now. Substitute, then as you can see here, the final answer we get current gain is 3.262. yes, the current is being amplified by how much? By 3.262. So for this particular common collector amplifier, let's say we have input current as 72 micron ampere. So now as we know, the current gain is 3.262. okay, so it is the output current is being amplified to this value following the current gain. So please take note that when we are considering common emitter amplifier before this, whatever Ri value straight away can be used to find for the voltage gain, and whatever R0 value you find from step number 1 straight away can be used to find for the gain. But for common collector, for the case of Ri, yes, it can be used, but in the case of R0, we cannot straight away use the Req value that we found from step number 1. Instead, we need to use some kind of test voltage, or we need to use the formula to represent the R0 value. Please take note about this, okay? It's important. Now let's have a look on another example of common collector amplifier. Obviously we know this is common collector amplifier because as you can see here, the load resistor is being connected at the emitter terminal, so we know the gain should always be positive. In this case, IC is straight away given, meaning we don't have to do the DC analysis. Beta is given, VA is given as infinite, okay, meaning R0 is infinity, we don't have to consider in AC analysis. And from there, if you use the IC value to find for the small signal parameters, you are supposed to get R pi GM, then obviously R0 is infinity. So basically for common collector amplifier, we need to use the modified small signal equivalent circuit. I'm not showing you how to get it. This is the modified version. So make sure you do your own self-revision to get this small signal equivalent circuit, the modified version, in order for you to proceed with the AC analysis. Okay. So then step number 1, we find for Req. In this particular case, we are not considering small R0. So that's why our Req straight away equals to Re. Then step number 2, remember we use KCL, okay, to find for I0 in terms of VBE. Then step number 3, obviously V equals IR, I we already found from step 2, R from step 1, so we can get V0 in terms of VBE. Then continues to step 4, we are supposed to calculate for RIB, which is given by this formula. Substitute everything, then later you can get RI, because RI is actually RTH in parallel to RIB, remember? Then next step, we can relate VBE in terms of VI using supermesh, right? So we substitute everything, we are having VI in terms of VBE. So considering the equivalent circuit of voltage amplifier model, where we already have V0 in terms of VBE, and we already have VI in terms of VBE as well. So we have AVVI equals V0. So substitute V0, which is in terms of VBE, and this VBE, we substitute it with VI. Okay, this VBE, we can have an expression in terms of VI. So that's why here this is VBE. Then substitute, leaving our AVVI, okay, in terms of VI, where we can slash it out to find for the open circuit voltage gain. So remember, since for this particular example we have a load resistor where we need to do voltage divider later at the output side, it is a must for us to calculate for the R0. We need to calculate for R0, where R0 is given by this formula, right? So once we have all the parameters here, all the values, we can substitute, then we get R0 is this value. Then from there we can find for VI, which is in terms of VS. For this particular case, since we are not having any resistor here, no resistor, where VI is actually just in parallel to VS, so that's why we can straight away say VI equals to VS. No need to do a voltage divider. Then later at the output side, for this particular case, for this particular example, we need to consider for voltage divider. Why? Because now we are having a load resistor RL. We cannot say our V0 equals to AVVI anymore. Why? Because it's not open circuit anymore. We are having RL. So that's why we need to do a voltage divider. You need to do voltage divider. Then remember, we are having AVVI, where AV we already found just now, and VI actually is just equals to VS. So we are having V0 in terms of VS. We get the ratio of it. So this will give us the voltage gain. Obviously, for common collector, remember, is always close to 1 because it is not a good voltage amplifier. Then let's have a look for the current gain, because it's a good current amplifier, remember, for common collector. So for the output side, we consider for the output current, okay, which is given by V0 over RL. Then at the input side, we consider for II, which is given by VS over RI. Then obviously we know current gain is I0 over II. I0 we have it in terms of V0, and II we already have in terms of VS. Okay, so substitute everything. Now you see we are having expression of V0 over VS here, which is actually our voltage gain that we already found just now. So we substitute here the voltage gain, then finish it off. So you are having current gain is 8.46, meaning yes, the current is being amplified by how much? By 8.46. So if we do piece-by simulation for this particular common collector example, as we can see here from the waveform, this is our input current and this is our output current, because it is being amplified by 8 something just now, right? So basically that's all related to chapter 5C, where we already discussed about common collector amplifier and its related examples. Okay, so use all the examples as your own self-revision. Try to do it on your own, okay? Okay, that's all. Thank you so much for watching until the end. May Allah bless whatever knowledge you gain from the video. Have a nice day. Bye.